So I see it is 12 noon, and with that, I'd like to officially welcome you all to the our Data Visionaries event. And yes, so thank you all for coming to our Data Visionary series on quantum computing. My name is Fred Popowich, and I'm the Scientific Director of SFU's Big Data Initiative, as well as your moderator for today. And although we are conducting this panel session virtually, the session was originally to take place at the Morris J. Ross Center for Dialogue in Vancouver. And with that in mind, I wanted to begin today by acknowledging that we were privileged to be doing our work in the unceded traditional Coast Salish lands, including those of the Squamish, Tsleil-Waututh, and Musqueam nations. And on behalf of Fraser University, I have the pleasure of welcoming you all to this Spring 2020 Data Visionary series. And yes, it is still spring by a few days. A series that is dedicated to bringing together pioneers in the field who are shaping and reshaping the world we live in. I encourage you to join in today on the conversation online over Twitter using the hashtags SFUBDI, as in Big Data Initiative, and the hashtag Data Visionaries. So about today, well, organizations are pioneering the quantum future and are very hopeful of how this technology could be used to better understand our universe and deliver breakthroughs in areas like drug development, encryption, and finance. Significant contributions from organizations, together with government-supported initiatives, make this field ripe for innovation. In terms of that, there is, as the quantum race proliferates around the globe, the question still remains, how quickly is this revolution happening, and how does it benefit the average person? And there's competing claims that can contribute to this hype around quantum computing as we continue to explore the breakthroughs, benefits, and challenges of quantum and that impact that it will have on Canadians around the world. So to start things off, though, we wanted to gauge your knowledge about quantum computing with a poll, which you'll be able to access if you're running the Zoom app. So this poll should be appearing on your screen shortly. And you can give you about 30 seconds to answer this in terms of this. So the question being, what would you say is your knowledge of quantum computing? First choice is, hey, I'm an expert. Second is, I understand it, but there's so much more to learn. Third being, I know a little bit about it. Fourth, I've heard about it, but don't understand it. Fifth is quantum what? Or you were looking for something else on a lunch break and you ended up in this room by accident. So give you a few more seconds to answer that one. So we've see that 3/4 of the people have voted yet, and I know that quite often people can't vote because of the kind of browser. So once the numbers stop incrementing, I will be officially ending the poll, and we'll see what category everybody is in. And we'll see who accidentally got into the wrong room too. So we're hitting it. 3, 2, 1. End of the poll. Okay. And in terms of the results, I'm going to share them there. So what's great is, and you notice I didn't invite our panelists to join in here. We don't have any experts. So clearly those are going to just be our panelists in terms of that. We had the two people that are sort of like me in quantum what, or maybe I'm slightly higher than that there. But you'll see that everybody's pretty much in the middle that, hey, know a little bit about it and wanting to find out more. And really when we see that a lot of people have heard of it but don't understand it. So I think this is the ideal place for us all to come together and have some of this discussion. So with that context, I'd like to, hopefully the poll has disappeared off your screen right there in terms of that. With that context, I'd like to introduce our panelists for today. So we have on our screen here, we have Stephanie Simmons. Stephanie is a professor, assistant professor, Tier 2 Canada Research Chair in Quantum Nanoelectronics from Fraser University. And she was formerly a PhD student in material science at Oxford University in 2011 as a Clarendon Scholar. Also joining us today, we have Silas Brownsey. Silas, since I told what Stephanie's previous role was, one of Silas's previous roles was as Associate Deputy Minister, Investment, Innovation, and Technology Division with the Ministry of Jobs, Economic Development, and Competitiveness with the province of British Columbia. And at the time this panel was originally scheduled, that was his role. Right now, he's Associate Deputy Minister for Strategic Planning and Land Use Division for the Ministry of Municipal Affairs and Housing. So we now want to figure out where that Quantum Institute is going to be housed. That's why I think we've got him in there as well. And finally, and last but definitely not least, we have Arman Zaribafiyan. Arman is with 1QBit, and he's been with them since its inception in 2013. And as the head of quantum computing there, he leads an interdisciplinary team of researchers and software developers who are exploring the applications of emerging quantum technologies and solving computationally challenging and solving some of these challenging industry problems that people are having there. So just before we get started, just going over a few of the housekeeping items before I turn things over to our panelists. We have prepared some questions in advance for them today. And throughout the session today, we invite you to write your own questions in the Q&A section on the screen there, assuming you have the Zoom app and are able to access it. And if you can't, feel free to just put it into the chat, and our people can hopefully get the question in there as well. And you'll have the option to vote up questions or ask, or like I said, or even write your own. And at the end of the panel session, after our prepared questions, we'll turn it over to your questions, and we will aim to have us all much wiser by roughly an hour from now. We will be all much wiser. So, so we appreciate you thinking of your questions as you're going along. And to get things started, what we're going to actually do is I'm going to allow the panelists to give introductions of themselves, because I just gave those brief introductions, and allow them to answer a question in a bit more detail. So Stephanie, we're going to start with allowing you to tell us more about your background and answer the question, what is quantum computing? Stephanie, over to you.
Sure. So thank you very much. So I'm one of the few people, or really early people, to get involved in quantum computing from basically my undergrad. Because it's a very recent field, as it were, right? So there are a lot of people that moved into it, but I got to start it from the ground up. I did my undergrad at Waterloo, where they had just started the Institute for Quantum Computing at the time. I did, as it was mentioned, I did my PhD at Oxford. My push, originally I wanted to program quantum computers, and then I realized that it was going to take a lot longer to build them than I thought, so then I switched to trying to build them. So my PhD and onwards, I've been working on the quantum hardware development, so the actual hardware that will allow quantum computers to really change the world. And then I did some work in Australia for a while, and then I started up here at SFU just about in 2015. So I'm on CFAR. I've gotten, in terms of my pedigree, I've gotten a couple Physics World Top 10 Breakthrough of the Year for the hardware stuff that we've been doing. And we're doing stuff that's based upon silicon. So it's kind of a dark horse bet compared to some of the other outfits out there. Intel's working on silicon, but a lot of the other main supplier or main manufacturers, including, say, D-Wave, working on a different system. So there's lots of different systems that are being in play, and I can get into all of that. But that's not what the question that was asked. The question that was asked was, what is quantum computing? And so when I get asked this kind of question, I try to bring it down right to the basics. Because when you think about what computers are really just physical objects that are manipulating physical bits, right? Like all the information that we have is all physical. It all is represented by the ones or the zero represented by like a physical thing oriented one way or another, or some other configuration. And so everything that we can do with computers that we have is based upon the brilliance that is silicon nanofabrication. And it's about manipulating things in silicon, really. But in general, information processing is about manipulating physical objects. And it was realized back in the 80s that if you paid attention to all the possible physical laws that are available to us, and not just the ones that we are accustomed to at the large scale, right, where like a thing rolls down the hill, that's called like classical mechanics. Those are the laws of classical mechanics of physics. If we start thinking about all the laws that are enabled by extreme areas of physics, such as quantum physics in particular, you can potentially do more. And let me get a little bit specific here. So if you have a particle, well, all particles are ultimately quantum at some scale, they can do things that you wouldn't otherwise expect at the ordinary scale. So quantum particles like light or electrons or these kinds of objects can actually exist in so-called superposition. They can be in multiple configurations at once, multiple incompatible configurations at once. It's the same thing as saying like this cat can be both here and in the next room. This is exactly how it works at the quantum scale. And that doesn't always mean cool. As I said, photons are at the quantum scale, and you can be in photons can be in two incompatible locations at the same time. So if you think about what that means from an information processing perspective, you could have a 0 and 1 at the same time, or rather in quantum superposition. That's not the only part. Like quantum physics has a whole bunch of laws associated with it. But that kind of already tells you that there's something there, right? In terms of the power that you can get. If you think about the total amount of information that could be contained in a small number of quantum particles, it's so much more than that can be contained in particles that are restricted to the laws of classical physics. So if you were to try and compare, it's basically 50 qubits. To encode 50 quantum bits or 50 qubits requires the same amount of processing power as the biggest supercomputers on the planet. 50 qubits, 50 quantum bits versus the biggest supercomputers we have. And this is because the information density of quantum systems is just so high. So in terms of big data, this is the so-called bigger than big, right? You can't really encode more than within a quantum system. And so there's this standard Moore's law that people have heard about. Okay, well, every X months you get to have some doubling of capacity. Quantum systems offer, in terms of information content within a quantum system, if you add 1 qubit, you double the information capacity or the size of that, informational size of that object. So huge amounts of, huge giant structures for a small number of quantum bits. And this actually touches on maybe one of the next points, but it also gives you a hint of the kinds of things that quantum computers can offer. Because some systems, like chemicals, are inherently quantum mechanical, right? And so if you're trying to simulate them using classical physics computers, which is what today's modern supercomputers are all classical physics computers, you can't do it because you can't compete with the information density that those systems have, right? So if you need a quantum solution, you'll need a quantum computer for a quantum problem at a minimum. And then there's all these other applications, which I'm not going to talk about here. But before I wrap up the answer to that question, I wanted to say one more thing. It's not as if you get this massive parallelism for free and then that's it. There's this other side, which is connected to the whole concept of Schrodinger's cat. So for those of you who've heard of Schrodinger's cat, I'll bear with me. The concept is that things in superposition, when you observe it, when the measurement is made, there is some snap. It can only report being in a classical value. A quantum object can't say, oh, I'm in superposition. It snaps to either one of the classical values. So for Schrodinger's cat, in the unfortunate superposition of a cat being dead and alive at the same time, when you open the box on that superposition, it snaps to either being dead or alive. And so the same thing happens for quantum bits. So you have to engineer your algorithms carefully so that when you look at something, it reveals the answer and not just a random string of zeros and ones, given that it could be in all of the zeros and ones all at the same time. So it's a complicated thing to juggle. People are moving on it really quickly. There's different scales that have been built of quantum systems that have been able to actually outperform the world's biggest supercomputers at some problems. And we'll get into that more as the panel continues. So I'll leave it there.
Great. Well, thanks very much, Stephanie. So that's why we turned it off over to the PhD in physics to give us that context, So now I want to move it over to Silas over to your introduction. You get the easier question, which is why is quantum computing important? So over to you, Silas.
Great. Thanks, Fred, and thanks to Simon Fraser University for hosting. Happy to be able to do it, albeit virtually, but I'm sure this will be just as stimulating a discussion as we'd planned earlier. And thanks to Steph for that awesome primer. I'm definitely not a tech person. I'm a career civil servant, And as Fred's pointed out, I've recently moved jobs, and that's what happens sometimes in the public service. And I get to try lots of different things, and I've had the fortunate opportunity to spend a bit of time with a portfolio that included the technology sector, and by extension got a little taste of what quantum computing is all about. Prior to that, I've had a variety of roles, including in Aboriginal relations, health, and the transportation sectors, and now I'm working in municipal affairs and housing, focusing on land use planning. So I have a varied background, but certainly not in the tech sector primarily. So my comments today will be kind of more from a layperson's perspective, touching more on the sort of the economic and job creation opportunities that we see perhaps occurring to BC now and in the future related to quantum computing. So from the province's point of view, we care about quantum for a couple of key reasons. First, we think BC has a comparative advantage already with a number of key anchor companies and some world-leading R&D that we can build on and use to grow the sector and develop a talent pipeline that will ultimately benefit British Columbians, our people and our economy. And the second reason is around the potential for quantum computing to help solve some problems and challenges that our foundational industries are facing and help them become more competitive and efficient. I think we're going to talk a bit today about application in different sectors, but it's certainly something that within the province we're thinking about. The application of technology to solve real-world problems that we face as a province. And it's for those reasons that the province actually invested $17 million over the next 5 years to stand up a new Quantum Algorithms Institute, which will bring together industry, post-secondary, and government to help achieve the benefits that I talked a bit about. This took enormous foresight on the part of my colleagues in government, as well as with our partners in academia, Steph being one of them, and industry partners to think about long-term opportunities. It was just created a few months ago. We're fortunate to have both organizations that are represented with me here on the panel as part of this endeavor. And we're driving towards a mission that will look to leverage our strengths to establish an ecosystem that features kind of broad participation across sectors and an inclusive approach to this core technology that will focus on talent creation and creating jobs and economic development. So it's an exciting time. I think we're going to hear a bit today about kind of what we're good at and where we might be going. But we're feeling kind of bullish around the opportunity from the province's point of view, and that's why we're here, and that's why I'm happy to be part of the panel. Thanks, Fred.
Great. Thank you very much there. And finally, it is Arman, over to you for your introduction and from your perspective on why quantum computing is important.
Absolutely. Thank you so much, Fred, for your introduction and also for including me in this very interesting panel. It's really my pleasure to be here today and with the other panelists here today to be able to discuss one of the things that I'm most passionate about. And thank you for giving me this opportunity. I'm Arman Zaribafiyan. I'm the head of quantum simulation at 1QBit. And as you said, I have been with the company since its inception. My academic background is in quantum information processing and particularly understanding the fault-tolerant hybrid quantum computation and the algorithms that we can run on fault-tolerant quantum computers. I'm a UBC alumnus and a student, and I have learned a lot from my supervisor, Professor Robert Rosen there at UBC. Let me tell you a little bit about my journey in quantum computing. I started in my bachelor's degree as an electrical engineer looking into classical information theory and its impact on the theory of communication. And then very soon I realized that I wanted to do something bigger and more interesting and newer, and I was introduced to quantum information processing and quantum information theory. So I started to focus on the information theoretical aspect of quantum computing in my graduate studies. And I was very lucky that early on in the process, I got introduced to the co-founders of 1QBit, which was the, at that point, the first software startup focusing predominantly on exotic computing platforms with a focus on quantum computing. And it was just a dream come true for me to be able to study quantum computing, quantum information processing, and also be able to find this opportunity to both learn in industry and also contribute. And that's my engineering kind of like background always kicked in and always wanted to push me from the theoretical aspect of quantum information to basically understanding its potential in industry and its applications, and kind of like bridging the gap between the rich state of theoretical research in quantum computing and what the industry needs and the applications, and being able to use it in real world scenarios. So for that purpose, the opportunity of working with 1QBit's co-founders since the beginning and basically going through that journey with them was a fantastic opportunity for me. Let me tell you a little bit more about 1QBit as well. 1QBit is now a collection of more than 120 scientists and software developers in different fields: physics, chemistry, computer science. And we partner with Fortune 100 companies, and we help them basically understand and work and use software tools to bridge the gap between the theoretical state of quantum computing and be prepared for the future applications of this technology. So now with that, let me tell you a little bit about how we think of bridging this gap, and especially why quantum computing is so important. And I think from our perspective, the key to answering that question is in understanding why do we even need to think about new paradigms and new forms of computation. And Stephanie beautifully described the foundations of this, in that our computers, as we know them today, and even how advanced they are right now, they are still inadequate and insufficient in solving certain categories of problems that we face in our industries and as humans. Let me give you an example that is very relevant to, for example, our discussion and these unprecedented circumstances that we are in, and also the focus of my team and my research at 1QBit. Let's look at the drug discovery and the application in bringing a new material to market. Bringing a new material to market, depending on who you ask and who you talk to, on average takes 10 to 15 years of hard research, and on average around $5 billion. Just to put things into perspective, developing Falcon 9 rocket that a few days ago or a week ago took two astronauts to a space station took 5 years to develop, and around a budget of like $400 million. So compared to that, when we look at, for example, drug discovery and bringing a new material to market, we are looking at a problem that is immensely and exponentially expensive in terms of the effort, the time, and the budget that you have to invest in that process. When we look a little bit closer into that process, we see a very stepwise approach in discovering new materials, but a significant portion of this process is based on trial and error. Basically, spending a lot of time building materials in the lab, trying them, failing, going back and starting from the beginning and doing the same until we converge. And the reason behind that is that, as Stephanie was describing too, our computers are not as powerful to be able to simulate a lot of these reactions and processes to save time and the energy and the budget that goes into that trial and error. Basically, if we have good simulators, we are able to simulate a lot of that in silico and in our computers, and just accelerate the process and basically change that trial and error process to a process that is based on and informed by accurate computer simulations. Well, this is not possible now because we just don't have the right computer tools to be able to accomplish these simulations accurately. And this is, for example, one of the areas where there is a huge opportunity in industry to be able to disrupt the process and to be able to use new paradigms and new techniques in computing to be able to accelerate a problem that is very important, especially in our in the times that we are living right now, and basically the difficulties that we are facing. So this is kind of like an example of why we are so excited about the potential of these emerging computing technologies and what they can introduce to our lives.
Great. Well, thank you for that context. And actually, that's very nicely leading into some of our prepared questions that we had here. So for the next, just more than about the next half hour or plus, I want to go through a few of the prepared questions, which will give, I know already I've been writing down other questions that have come up based on what I've been hearing from. So but I will make sure that we will be turning it over to our audience for their questions. But for our first prepared questions, like I said, builds on what you were just talking about there. What are examples of industries that can benefit from quantum computing? And how do these benefits trickle down to consumers and workers? So given that Stephanie's had the longest time for her voice to recover, I'm going to put it over to Stephanie and asking her in terms of if she wants to, from her perspective and from given like her background very much in the hardware and the physics aspect of it, how you see that unfolding in terms of examples of industry that will ultimately benefit from quantum computing. Stephanie, over to you. I think you're muted.
Thanks so much. Yeah, sure. And so it's a little bit like asking, well, what does the magic 8-ball see? Because it's the same sort of question that you could have posed to people back in the 50s when they first developed the solid state transistor. So I don't know if anybody here is intimately familiar with that story, but basically the industrial motivation for the transistor in the 40s through the 60s was really the hearing aid. So there's this big giant push that, oh, let's make a transistor so we can make a hearing aid. And that's the industry that it's going to disrupt. And you wouldn't have predicted Facebook based upon the push to have a transistor hearing, right? So it's, so whatever I say going forward in terms of industry, yeah, we can point to specific use cases that are known now, but I wouldn't necessarily think of that as an exhaustive list because of course these sorts of things tend to get away from us. Especially when you start basically commercializing a new branch of physics, which is what this is, right? It's the same story that happened when when semiconductors took over, and now we have the entire information technology network. When we commercialized the branch of electromagnetism, the physics branch of electromagnetism, now we have like plugs that are just in the wall and boring, and you don't have, webinars and big data series on electricity coming out of the walls necessarily, right? So it's there's a lot that's going to come that we can't predict right now. But having said that, there are some things that we do know. And the one that attaches, it's just so plainly obvious, is the one that we've already mentioned, touched on a few times, is chemical simulations. Those are like inherently quantum, and there's just no other way around it. We have to do it that way if we're going to do it properly. But really, when you start thinking about the kinds of problems you want to think about categories of problems that are that fit into a couple of categories, and which is not to say that all problems in these categories can be solved by quantum systems, but these are the ones you'd look to try and see like the kinds of major disruption, because there's a known so the categories are those that require the temporary use of that giant computational space that I was alluding to before. And so you have that giant access, but then the answer has to be relatively succinct, because as we're talking about the Schrodinger cat side, the answer is only going to be a classical bit string, right? So it has this giant computational space, but then it reduces to like this very succinct answer. And so a lot of problems that are tackled in high performance computing these days do fit into that category. For example, searching, right? So if you're searching for something, you want to find one answer. It's a succinct thing, but you have to have looking through a whole giant list. And there are things such as Grover's algorithm, which is a quantum algorithm, which offers a speed up over the best known classical algorithm. So if we had that quantum hardware, we would be able to do that a lot faster. And so there's you could point to that. There are, so that categories where you're searching, needle in a haystack kind of problems. Other problems that fit into that kind of category are, say, encryption, breaking encryption schemes. That's another one that quantum computers are quite famous for having exponential speedups in terms of algorithms. And so there's a whole side to that I can get into if anybody is interested, because we're not trying to break the internet. We actually have something better. But anyway, I can get into that if anyone's curious. And similar to those kinds of needle in a haystack problems, you also have problems where it's kind of like heuristic. So you're looking for properties of an entire giant set, and you're looking for, say, minimization, that kind of thing, right? So you're taking a look at heuristic properties, optimization, logistics, like that kind of stuff, right? So those kinds of properties where you're taking a look at making use of large data, or large parameter spaces, and coming up with succinct answers. And so if you're talking about industries, I mean, that basically touches on all industries. So if you think about it, any industry that makes use of some amount of optimization, or, generally this kinds of problems that are tackled with high performance computing these days are usually in those kinds of categories, which is not to say that they all have, quantum variants, which are better, but the other side to it is we don't yet know, right? We have made a bunch of progress in terms of known algorithms that offer exponential speed up if you have a so-called universal quantum system. So we already know, without having a working large-scale quantum system beyond 50 qubits or so, that these algorithms can and will exist, and it's inevitable once this hardware gets up, and will disrupt all of the industries that rely upon those kinds of algorithms, right? Drug discovery is one of them, logistics, optimization, finance, I mean, just the whole lot of it, right? As well as just research in general, right? How much is high performance computing assisted research, right? So all of that will happen, and that's before we even have a system where we can play, right? Before we actually have people that are brought up running these things, in high school, and get the familiarity with them to get the intuition for the next kinds of algorithms that are going to come up. There's also, I imagine Arman will speak to this a little bit more, but there's a whole new category of quantum algorithms that are these kinds of hybrid algorithms where we're using sub-algorithms that would be based upon a quantum processor to accelerate things like AI, and those sorts of kind of hybrid schemes where you can make use of quantum schemes, but not for the full part of the process, even just for a part. And in that sense, you could touch on like most high performance industries. So it's going to be one of these sorts of things where it remains niche, and then very suddenly it's going to become critical to the operations of all computing needs in the high performance scheme, right? So to some degree, you have to be aware of where the limits are. So it's fun because we get to ride that out. Like, I know what my career is going to look like. It's just not clear exactly when that major event is going to be happening. It'll be a very gradual but sudden thing. So I think I'll leave it there.
Okay, great. Actually, and it's great to have so much in your career to look forward to.
Yeah.
This is great. Yeah. So, with that in mind, I'm turning that same question over to Silas for, from his perspective, examples of industries that could benefit from quantum computing, and feel free to elaborate on how that might even benefit the ordinary consumer and worker too. So, Silas, over to you.
Great. Thanks, Brett. Well, I think I'll defer to Arman and Steph with respect to immediate application of the technology. I mean, obviously it seems that the possibilities are maybe limitless. Areas where we have big, complex problems, this could potentially help. One of the things we're sort of grappling with as we stand up a new institute is to really identify real world industry and public policy and research problems that could be solved more efficiently with this technology, and then start to prove out the value proposition. But before we even get there, though, I think there's another opportunity, or maybe a challenge for us, is for us to get there and for this to become relevant. I think we need to make sure that we are bringing people along and making it understandable. industry needs to see the potential for the technology to help them and some of their wicked problems. And that sometimes takes people within those companies that are actually conversant in some of this stuff. And we're starting to see that a bit, but obviously more work to do there. We need students who can see career paths and start to build out our talent pool here in BC and across Canada. It really boils down to, why is this something that I should care about when I'm looking to make investment decisions to help my business out. So the opportunity, I think, is we've got this incredible talent pool here in BC who can help and are already doing this work. And so, how do we demonstrate why this is important to BC, and then more importantly, why BC is important to the larger quantum ecosystem? Because I think we are. And there's we're part of a larger network across Canada, obviously, and even with our cousins down in Pacific Northwest in the US, but BC has got something going on here, and we should exploit that. And maybe my last point would be, I don't think this should be seen as like a high-tech thing. There are practical applications that can make good business sense for a whole range of industries. And so that starts with a bit of a call to action, and using the use cases we have now, and doing our best, I think, collectively to ensure that people see the potential and are willing to sort of get into the game. Yeah.
Great context. And I really appreciate you raising the talent pipeline piece in terms of this, because again, to sort of echo some of the things that Stephanie mentioned with respect to even from the hardware point of view, the creation of the transistor, from the thing of it, what way it was just not that long ago with technology or computing. It was like there never used to be departments of computing science, back all those years ago. And many people realize that, it's not just the science behind it, it's an application of the science and how people are going to use this in their ordinary careers and ordinary jobs. So I think that, again, learning from what we've seen in the past, I think it's really important to have as much vision in terms of what we've learned from the past to inform our future. So with that, I'm going to pass it over to Arman so that he can give us speak to this question about the examples of industries that can benefit from quantum computing and how that might tie into ordinary consumers and workers. Over to you, Arman.
Yeah, absolutely. Thank you, Fred. I think Stephanie and Silas touched on this question very well, in that I think the way we look at these applications and we try to bridge the gap, we see industries and particularly problems that are perhaps closer in line to benefit from these technologies earlier than others. But really, when we look at the fundamental problems that this new paradigm of computing can address in terms of optimization, in terms of simulation, and in terms of its applications in accelerating machine learning models, when we think about the fundamental mathematical problems that these computing platforms can address, then we see that after that inflection point, it's easy to understand how ubiquitous basically their applications can be, and what industry can we name that they don't have an optimization or an engineering trade-off problem, trying to understand optimize the kind of like the routing of Amazon's delivery trucks. That's a huge optimization problem. Solving traffic congestion problems. These are like problems that governments deal with right now. I don't know, simulating inherently quantum mechanical systems like molecules, like drugs, like new materials. Solving a carbon capture problem and finding new catalysts to basically accelerate these processes. I think when you look at the fundamental problem that these platforms are able to tackle, then you will very soon realize that the potential impact of this can be huge and can touch many different industries. But we do believe that, as Stephanie described as well, we do believe that, for example, as this technology is basically coming out of the lab and becoming more mature and getting ready for prime time, we think there are areas that are going to be in line to benefit from these advancements earlier. Like, for example, studying systems that are inherently quantum mechanical. Like, let's use a quantum computer first to study other things that are quantum mechanical. And the good thing is that our nature is quantum mechanical, physics is quantum mechanical. So suddenly we see that there are a lot of opportunities, and it's not just it's not just a theoretical, abstract, scientific question that we want to answer. It also has huge implications in industry as well, like the examples we described in terms of simulating molecules. And that's why we see, for example, companies like Dow Chemicals, our partners, companies like Biogen Pharmaceuticals are among pioneers of adopting this technology, and first and foremost trying to come and say, hey, computing is very important for our business, and there is a new paradigm of computation that has huge applications in disrupting how we approach our computational problems. We want to understand this. We want to be prepared for this, and we want to look into this. And there are some of these companies, like, for example, especially in materials development, as I described earlier, they have product life cycles that are 10, 15-year processes. Like, they are already planning for what's coming up next 10 years from now in the pipeline. So for them, adopting a new technology and a new paradigm of computation is not an unfamiliar practice. And I feel like in earlier stages, materials innovation is going to be one of the fields that's going to be hugely disrupted with this technology. And then further down the line, as these systems are more mature, financial services, industries with complex logistics problems are among those that would be kind of like on the front line of benefiting from the applications of quantum computing.
Great. Thanks very much, Arman. And you've actually, in terms of that first question, it's opened up a lot of questions. I see other people are already posting questions in the Q&A section. So just a reminder to people, please continue to post the questions there. We'll be getting to them shortly, and feel free to upvote other people's questions if you don't have one yourself, or you can, sorry, you can't downvote. I don't think we have that feature implemented here right now. But you've spoken the notion in terms of the different sectors and examples of industries. And the one theme that's been discussed is how variable that is. Like, some of these industries have very long time frames for needing to make decisions, or even taking actions require a long time. Other industries, you need to make like, are we able, for instance, to get a vaccine next week? No, that's not possible in terms of some of these things. So I want to use this as the bridge to our second question, which was how long until quantum computing is, we said, relevant? So when is the average person able to benefit from it, and when can organizations expect to start using these technologies? And in terms of that, I'm going to go to, actually, I'm going to go to Stephanie, and then probably come back to Arman, and then I'll let Silas chime in on what he thinks of our other two experts in terms of that from the government's point of view, whether they've got it right. So Stephanie, over to you in terms of how long until quantum computing is relevant.
Sure. So I'm also going to be sneaky and answer the first question on the Q&A, and also answering this question. So because it is relevant. So there are quantum computers will be able to break modern encryption. So modern encryption, i.e. the encryption you use to send your bank details over the internet, that's using a scheme usually called RSA, wherein it relies upon the fact that it's very difficult to factor the product of two prime numbers if those two primes are very, very big. You're basically having to hunt through, it's this needle in the haystack problem, right? You're having to hunt through most of the primes that exist to try and find the one. It's an asymmetric computational problem, because if you know what one of those primes is, you can just divide through that big number and have the other one. And that's basically the math that underpins most of modern encryption, the reliance upon the fact that it's hard to compute a certain thing. And so in terms of how long is it going to be until it's relevant? Well, it's relevant now in that it's known to the community that there are actors that are saving encrypted transmissions now in the hopes that in some future time, quantum computers will be able to break that encryption. in a brute force way. So it is relevant in that scale. It's also relevant in that, you know, as I mentioned, we've just passed this tipping point, this kind of quantum hello world, where we've now, a couple of different labs have something on the order of 50 qubits, and Google very famously demonstrated the ability to use those 50 qubits to outperform something that no classical supercomputer could do on the similar timescales. So, I mean, it is relevant now, it's coming. It's the same question you might ask is like, when was the internet relevant? Was it 1993? Was it 2003? Like it's going to be a transition, but it is starting now, and it is inevitable. The time scale by which it'll affect everybody. I mean, it'll affect you before you realize it, in that it's going to be an algorithm that perhaps Amazon uses to predict a better product for you to click on, right? Like you won't necessarily recognize when it's affecting your life. It'll just kind of sneak into the way that high performance computing is kind of taking over a lot of what we do. So in terms of the encryption, yeah, that normally puts a couple of alarm bells off for a bunch of people. Fortunately, quantum technologies also offer what's called quantum encryption. And there's also the quantum safe encryption. So right now, NIST is going through a competition to try and find something that isn't RSA that people can rely upon as an encryption tool that quantum computers cannot break. That competition is ongoing, and at the same time, the previous lead in that competition has been since broken by a quantum algorithm. Again, this is before we have a quantum computer, right? So there is so-called quantum safe encryption. They're going to try and find something that a quantum computer can't break. There are other things in that category that are promising. But ultimately, the provably secure thing is actually so-called quantum encryption, where we can make use of the fact that you can't, by looking at a quantum system, if you interact with it, you affect it. And by basically that means you can't copy quantum information, because that act of copying just is not permitted. And so this is one of the laws of quantum mechanics that you can rely upon to form a new kind of encryption, which is a physical encryption. It's not relying upon the fact that it's hard to computate or to compute something. It is a physical object. It's related to a physical object. And so therefore no quantum computer could break it, even though it's quantum encryption. And so that exists. That's actually been a technology that has been deployed for 20 years now. What is stopping that from being deployed globally is the fact that it only works on short distances so far. They need technology like the technology we're working on down in the lab to build quantum repeaters to basically extend that to a global network. And so there's a bunch of different labs that are working on those kinds of hardware goals to be able to unlock this for a global encryption scheme that could withstand any future quantum computer, as well as all of today's classical computers. So I hope I got 2 in 1 there.
Yes, you did. A wonderful way of drawing in, and thank you very much for the question from the audience there that we were able to draw into our questions there. I'm going to turn over to you, Arman, for you to speak to this a bit more before turning back over to Silas.
Absolutely.
So how long until quantum computing is relevant? This is a reminder for everyone what we're talking about. Yeah.
Absolutely. So the way I always try to approach this question is, first of all, we have to understand what relevant means. In that, to me, I completely agree with Stephanie in that quantum computing is already relevant. And in addition to what Stephanie has mentioned, I want to put a new angle into it, in that at the same time that we are waiting for the hardware technologies to become mature, there's a lot that can be done on the algorithmic and on the software side of quantum information and quantum computing. And there's a lot of progress that has happened in the past few years, and also in basically understanding new algorithms. I think what quantum computing, or the progress in quantum computing, taught us is that classical computing is not the end of computing, and we can do better. And already you see new algorithms that are being developed classically that are called this category of quantum inspired algorithms that are outperforming the state-of-the-art algorithms in their own field. One of the kind of like one example is, for example, the kind of quantum inspired algorithms that were developed for the problem of kind of like a machine learning problem that involved recommendation systems, and they started there, and it kind of like was expanded and generalized to other algorithms as well. So to me, based on how we define relevant, I think quantum computing is already relevant and it's already kick-starting new avenues of computation, especially in terms of algorithmic development and software development. That is really interesting, that is already showing some progress over the state of the art. Then on the quantum hardware itself and on the experiments on the hardware, I want to basically say this, that it's hard to put a number on this, because obviously a lot of factors are in there, and a lot of people use the convenient 10 years example because it's kind of like short enough that you can see it in your lifetime, but long enough that you still have time to make progress. I don't want to commit to a number, but what I can say is that quantum computing scientists are continuously surprised by the fast and accelerated pace of progress in this field. If 2 years ago or 3 years ago, someone asked us that soon one of these hardware providers is going to hit a supremacy milestone, that for the first time, quantum computers are able to outperform the largest supercomputers that we have access to even on a like limited synthesized problem set, I can guarantee you that even the most optimistic scientists would have said, well, that's still like 10, 15 years, 20 years away. But that happened last year. And basically, I guess what I'm trying to say is that we are continuously surprised by the pace of the progress. And we don't need to wait for the hardware. There's a lot to be done on the software side and on the algorithm side. So to me, when we look at this two-pronged approach of pushing the hardware forward at the same time as the algorithms and applications and the software, I see quantum computing already relevant and already disrupting certain industries.
Great. And so thank you for that context there. And just to finish up this question, I will have the last word on this question before we move to our final prepared question. Over to you, Silas, for your thoughts on how long until quantum computing is relevant.
Thanks, Brett. I certainly won't put out a number. I mean, I think what you're hearing from the panel is it's relevant now. You know, we have the companies here in BC that are already, you know, playing in the space and working with industry. And I think the challenge is for the average person, if this is about the average person, they may have heard about this, they may have read some articles, they may have seen there's like an arms race for quantum supremacy. Most people have no idea what that actually means or why any of this matters to them. I think to have the average person see this as relevant, you'll hit a bit of a tipping point once we start to see kind of problems of the day or pocketbook problems benefiting from this technology. And I think going back a couple of minutes ago, Arman listed a whole bunch of industries that could potentially benefit, right? If we think about congestion and traffic optimization, climate policy, thinking about some of our resource industries and our mining sector, financial services and insurance, logistics kind of writ large. I mean, those are all kind of things that people encounter, whether it's in their personal lives or in their professional lives. And once there's some stories, or you hit a critical mass of stories around breakthroughs in those areas, then I think it starts to become more relevant for the average person on the street. And that's starting to happen, and that's exciting.
Great. Thanks very much for that context there. And yeah, it's always safe not to have numbers. Every time any prediction I've made, never comes through on time. But for a quick question then, before we open it up to the questions we've been getting from the audience, the last question we had prepared was, and you've already, all of you have started to allude to a bit about this, what would quantum computing look like in the workplace? And in terms of that, yeah, so Arman, I'm going to start with you on this one there, and then we'll go to Silas and Stephanie, to finish on that one there. So that way, yeah, Stephanie will have the last word on that question. So Arman, over to you. What will quantum computing look like in the workplace?
Absolutely. I try to be concise. And this is an interesting question because there are different ways to interpret it. Like, would it be the workplace of a quantum computing engineer or a generic workplace? But I would address it this way, and this is kind of like also overlapping with the second portion of previous question as well, very concisely. We are lucky that quantum computing is making an accelerated progress at the same time that cloud computing is also becoming very ubiquitous and popular. And the way I would see this is that in a generic, basically, workplace, accessing the potential of quantum computing will probably be through the cloud. In that, I saw there was one question in the audience that when can we have a small enough and like economical enough device to be able to buy and have it in our house? Well, you probably won't even need to do that, because your laptop or your phone can already connect to a quantum computer through the cloud. And some of the organizations that we are talking about are already pioneering this. There are organizations that are already providing quantum on the cloud, like Microsoft, IBM, and other organizations. So I think the access will be very similar to how you use cloud computing resources that, for example, other provide other advantages. But also the other thing that I wanted to say is that for an average person, the way I envision it to be useful is that sometimes you need in the workplace to interact with the quantum computer to benefit from its future potential in computing power. But sometimes you are benefiting from that without even knowing it, in that, for example, you are buying a drug that is a lot more economical, for example, or you are having access to these materials that are kind of like a lot more economical, or for example, you have less congestion on the road, or a Google map that has a much smarter, basically, ways of suggesting better and less congested routes and faster routes. So sometimes the kind of like use and the applications will also be indirect.
Great. Okay, going over to Silas, in terms of your perspective on that question.
Thanks, Fred.
What will it look like in the workplace?
Yeah, thanks, Fred. So sky's the limit, I guess. I mean, I think Arman's done a nice job there. Maybe what I'll say here briefly is I think maybe we have an opportunity to really explore what that looks like here in BC. Its application in workplaces and industries. We've got companies in research. We have a new institute that is going to bring together a bunch of these players, and obviously some alignment with partners across Canada and here in Cascadia. So, from a provincial policy perspective, we're interested in seeing the growth of technology and innovation generally in all sectors, in all workplaces. It's not about being a high-tech sector and everything else. That's an unfair comparison, I think. So, where we can demonstrate relevance, we've talked a bit about that, and value propositions in areas that aren't traditionally seen as high-tech, that'll be success in my mind. It's important, though, to not lose sight of some of the larger policy challenges, I think, in this area. And that's around retaining things that we actually built here, right? Whether it's companies or IP or people, we want to make sure as we're growing this sector and expanding our footprint and seeing this sort of proliferation into all sectors and workplaces, that the things we build here, we maintain some durable connections to BC and value for British Columbians. So that would be kind of my closing thought on that piece, Fred, and pass it over to Steph.
Okay.
I'm just gonna stop. I'm just gonna say I'm just not gonna answer the question. Basically, the answer to it is fine. And we can turn to some of the great Q&A questions in the time remaining.
I think that's a great idea too, and seeing already some of them been answered, like the quantum computing and the quantum in the home as well. So just trying to get the QA to come up here on my screen here. So I'm just They just disappeared off my screen here for some reason here. So Steph, since you have it hopefully in front of you right there, why don't you take a look at the top? I remember what the top question was a moment ago before it disappeared. So over to you to answer that first question, then we can ask our other panelists.
Yeah, so the top one that I see right now are what are the potential dark sides and risk about quantum computing. And I mean, the response is that it's a technology, right? And like most technologies and most branches of physics, you can use it. It's how we use it is, that's up to the users. And we do have to, be, adults about this and responsible. In the same way that when you commercialize the branch of nuclear physics, you get nuclear power plants, but then you also get nuclear bombs, right? Like it's how we use it is up to us. Some of the technology sides, the encryption and communication side, I mean, that's going to be something, and how that plays out is going to be very interesting. Because there will come a time where quantum computers become sufficiently powerful, but it's not yet announced. I think that these sorts of things will fall under some government programs, black ops, because of it is basically the nuclear option when it comes to information security. And on the other side, that unhackable encryption side is also within government, within some branches of defense, at least seen as a threat, because then you can no longer do the kind of deep packet inspection that people have become accustomed to within the security agencies. So there's it's going to be that's an interesting side of how it plays out. In terms of just computational power, I mean, it's how you apply it, right? Like you can imagine the same sorts of discussions that are happening around AI and data mining and privacy, they all apply to any high performance computing system where you have that kind of power. It'll also be an interesting geopolitical situation when those machines become available and who gets access, right? So I don't think it's a dark side inherent to a technology. It's just we're human beings, and when new technology comes along, we have to be responsible.
Great context. Anybody else want to add on that, Arman? You care to add on to that one, or she's covered it well?
I think that was a perfect answer. Yeah, completely support that.
Great. So, Silas, anything else to add before we go on to the next question?
No, all good.
Okay, and in terms of this one, the next one that's the highest ranked there is, why is BC becoming a one-stop shop for quantum? Why don't we start with somebody from the province? It said BC in it, so we have to start with somebody from the province of British Columbia in terms of that. So, Silas, want to start on that one?
I'm sure it's just something in the water, Fred. It's a good question. You obviously have, Steph talked a bit about her trajectory and sort of being at the forefront of some of this research. And you've got research colliding with sort of commercial ventures. And for whatever reason, we have a bit of an ecosystem here. And I think some of that speaks to, foresight in terms of, early entrepreneurs and researchers, and some of it's probably a bit of happenstance. Some of it's geography. I'd actually be interested to hear what Arman and Steph say about it. But from my point of view, and I've sort of hammered this home a few times, we have an opportunity here if we want to drive it forward, and the benefits could be multifaceted if we really do take advantage of this point in time and the advantage we have at this point, and take that forward, and who knows where it'll go. So. Sort of a waffling answer. I don't quite know. I do know that we do have something going on here, though. So maybe I'll ask my two esteemed fellow panelists to see what they think.
Okay, Stephanie, I see you're unmuted, so it's over to you.
Sorry, I just forgot to mute from the last time. Yeah, I mean, I came to BC because it was this hub, right? So as of a couple of years ago, it was the greatest concentration of quantum engineers in the world because of places like D-Wave and 1QBit. And there's now a huge acceleration worldwide because everybody wants to be at the forefront of this now. But basically, Canada invested in this early. When I started at the Institute for Quantum Computing, it was the only global institute for quantum computing. And now there's a bunch. And so having that early lead means that you have a lot of talent and capacity, like the fact that you have local venture capital firms here that understand quantum computing to some degree, or at least familiar with it, like that's just phenomenal, right? We have an edge over everybody else. And so at least on the commercialization side. So one of the beautiful things about the Quantum Algorithms Institute is that it's really going to round out the package and bring on board a full suite of talent on the academic and the industrial side to complement the kind of hardware efforts that we already have going on. Like SFU, for example, has set records for the best qubits in the world at room temperature and low temperature a couple of years ago. That was one of those big breakthrough things. So SFU is outperforming, you know, Harvard, MIT on this front, right? So it's kind of one of these special situations that you have a place where you can recruit around from the whole world, and everybody wants to live here, and everybody wants to do these cool things. And so if you can have all that work, then yeah, let's use it, let's leverage it and build something wonderful.
Okay, great. And Arman, why don't you see what you can add to that one there before we go on to the next question?
Absolutely. I just want to briefly say that I think one of the reasons is because of people like Stephanie, actually, at SFU and at UBC. One thing to notice is that Canada is actually, as a country, a pioneer in quantum technologies and quantum computing, with like all over the country, but really in like three main hubs: at Waterloo, with IQC, at Sherbrooke, with Institut Quantique, at in BC with UBC and with SFU, and also in the private sector with D-Wave and 1QBit being kind of like the first commercial quantum hardware and quantum software developers. So I would say that it's actually, we are very lucky that we are inheriting kind of like a very strong foundation and pioneering foundation in quantum computing. Like there was a saying that like anyone who's a name in quantum technologies and quantum computing at some point spent their graduate life somewhere in Canada. And I think that already kind of like demonstrates the impact of like Canadian education and Canadian research in the field. And I think we are lucky to be able to in that position. I remember that early on at 1QBit, we were worried about finding talent and being able to tap into world-class scientists and researchers in this field. And then those kind of like problems were very easily solved because we realized that we are connected to a kind of like a huge resource at UBC, at SFU, and that's why like I'm proud to see that for example, 1QBit has become a successful local startup based on a lot of the graduates who are coming from Canadian universities. So I would say that there's a strong benefit in having access to that foundation and to those programs. And as my co-panelist mentioned, I think the next chapter with QMI, with Quantum Algorithms Institute, is going to be really exciting for the future of this quantum hub on the West Coast.
Yeah, and I appreciate you putting that context in there. We're going to go into a rapid fire range of questions right now in terms of some one thing that might answer several people's questions. With the Quantum Algorithms Institute, that's where aspects of training are going to be taking place, as well as I understand that Stephanie would speak more to that in terms of that when we have questions. So just for 15 seconds, Stephanie, so quantum just for graduate students? Is it for undergrads? Who is it all for?
Yeah, so the Quantum Algorithm Institute is going to do the full range. It's going to tackle the full talent, and it's also going to think about bringing on board the academic researchers needed to do the kind of hands-on research that is needed to really anchor that talent. So it's going to be the full suite.
Fantastic. Okay, going through the quick questions here again, and I'll try to pick on some people, or feel free to raise your hand if you want to answer it. So how much quicker could quantum computing make analyzing viruses like coronavirus for achieving a vaccination? All right, who wants to answer that one? Raise a hand.
I can quickly answer that. I think we are very excited about the potential of quantum computing in simulating quantum materials and materials in general. I should say that because it's a sensitive topic, I should very firmly say that I don't think this technology is still at a point to be able to make a meaningful impact on the current situation that we are experiencing. I think there's a lot of exciting progress in the field and addressing quantum simulation, but I don't think we will have like quantum computed vaccines for coronavirus. I think there are already existing technologies that are being leveraged, and I think those are very well advanced to be able to address that. But in future, hopefully in future, we will be in a position where by tapping into the potential of this technology, we will be a lot better positioned to bring a lot of the steps in the material discovery, drug discovery process, do it in silico, in simulation, and accelerate it exponentially using what quantum computing can offer.
Okay, great. Next quick question. Are there moves to make quantum computing more accessible and create products, packages for people so they become the basic tools of the future? Steph, a quick response to that one?
So yeah, I mean, you can go into any hardware supplier will have it. Amazon also has a quantum web services, and Microsoft is trying to do something similar for theirs. And they're all trying to do various levels of the stack. So basically packaging. The thing with the quantum resources we have so right now is that they're so precious that you really have to go back and think about computing in the way that people were thinking about in the 50s and 60s, where basically every single operation matters. And so it's a much more it's a more complicated problem where you have to make use of every resource along the way and not the layers of abstraction, which are actually a little bit wasteful when it comes to resources. So there are efforts underway, but it's going to be ongoing.
Great stuff. Next question. What is one of the biggest obstacles that quantum computing currently faces or will face in terms of its development and construction? Who wants to answer that one? Okay.
Yeah, I mean, I'm sure Arman has comments on this too. So basically, there's still a gap between what's needed for fault-tolerant systems and the applications running those fault-tolerant systems. So there's giant overheads right now. So if you wanted to run something, even though you have these, the size of 50 qubits is as enormous as it is. Actually, an interesting stat is the size of, I can skip that one. Yeah, it's going to be, it requires a lot of work on both the hardware and software side. It's going to take people that are getting better at running fault-tolerant systems and fault-tolerant design of algorithms that can then just be pressed like a button, as we were asking in the previous slide. And then on the hardware side, we need to get better systems. And that's one of the things that I'm focusing on. It's basically the hardware that's going to allow this all to work. And so I'm working full-time on that exact problem, trying to get the systems that have the best performance capabilities engineered into systems that are able to support these big fault-tolerant algorithms, and then having also people working on the fault-tolerant algorithms to make them less needy in terms of the total resources account.
Perfect. Okay, and the final question here in terms of, I found one. Are there any incubators or grants for quantum computing startups in BC? Who wants to answer that one?
I can as well, unless Arman wants to say something.
No, please go ahead.
Yeah, okay, so there's CDL, which has a quantum stream. CDL is specific to that, but I mean, the thing about incubators is that this sort of stuff, the people that are very good at training up quantum people, you really do want to get into the research side and get good at it and understand what you're dealing with. An incubator might not be enough. So you really do need to get hands-on into the technology through either work with an existing company or through a research effort, get involved, and then from there you'll have a much better chance of actually producing something useful. So it's not something that you can really do a boot camp on, and although there will be boot camps that exist, you won't get the kind of depth you need to really make a big impact. But having said that, there are programs like CDL that have quantum streams that you can take a look at.
Yeah, great. Okay, and on that note, I see we're almost out of time here, so I want to start to wrap things up by, we're going to bring up one more poll while we do the wrap up here in terms of that. So while that poll comes up, I want to thank all of our panelists for participating today, and really want to thank not only our team there for delivering this, but for all of you participants coming up with all these great questions, and everybody staying till the end, as long as I promise to finish on time. So our new question is, what would you say is your knowledge of quantum computing? And now that you've seen all of this stuff. So I'm seeing the numbers coming in now. So we definitely have much more knowledgeable people here. So we have no quantum watts yet. So I didn't, in terms of that. So I'm going to end the poll in just a few seconds so I can see the numbers coming in. And while people are voting there, aside from thanking our speakers today, on behalf of the SFU's Big Data Initiative, I'd like to thank you all for joining in our first online version of Data Visionaries. And at the Big Data Hub, we pride ourselves on engaging with the community on all things data, whether they be events like this one, supporting new collaborations, or even helping people with their training or talent needs. And hopefully we're able to even help people out there in terms of having questions about talent and quantum, that yes, there now is a Quantum Algorithms Institute, and yes, there are going to be ways that anybody can, you know, study quantum as well. So I'm happy, even in terms of our own training, we're launching our online data fellowships AI training starting next month. So I guess we're going to have to see, maybe a year from now, we'll be having our data fellowship quantum training being offered a year from this summer. We'll have to talk to you all about that in terms of this. So I'd like to thank you again for joining us today. And as we can see now on our poll, which is on the screen there, people are definitely understanding much more about it. Nobody's an expert yet, because if we were an expert, we wouldn't need the Quantum Materials Institute, you know, at UBC, we wouldn't need the Quantum Algorithms Institute at SFU, we wouldn't need the strong province. We are already a destination for quantum, and hopefully everybody is a bit wiser today. Thank you all again for joining us, and looking forward to seeing you at a Data Visionaries event in the very near future. Thank you very much, everyone. And we'll leave on the screen for you to see how to contact us if you wanted to be able to find more questions or answer questions. And unfortunately, we weren't able to get to all your questions. Thanks very much, everyone. Thanks.